Hello and welcome to this look at an applied calorimetry question on Q equals mc delta T. Firstly, I'll review two laboratory practical methods for measuring enthalpy changes that are commonly used in A-level chemistry laboratories. So the first one is measuring delta T for a reaction taking place in aqueous solutions such as delta neut H or delta RH. This means the water itself is heated, and you'd set it up something like that with two polystyrene cups, one inside the other, to try and minimize heat loss. So what's happening here is that the reaction mixture, let me just get my laser pointer, there we go. The reaction mixture is dissolved in water. So the water itself is the surroundings that absorbs or loses heat. So therefore the thermometer is measuring the temperature of the water in situ. And the other type is where you burn a fuel externally to the water. So the fuel is underneath and the water is clamped in a container above the burning fuel, and the thermometer is clamped so it's suspended inside the water, so it measures the temperature change of the water. So this is measuring delta T for a combustion. So M is going to be the mass of water in the beaker or container, that's Q equals mc delta T, that is. And what happens is the difference in mass of liquid fuel before and after is used to calculate the moles combusted, e.g. N. So reminding you of the Q equals mc delta T calculation, both methods will involve the following practical and calculation steps. So you measure delta T to allow calculation of Q in Q equals mc delta T. You measure M as the mass of water heated, so 1 centimeter cubed of water is 1 gram. Then you calculate N as the number of moles of reactant or product being used or made. And you finally calculate delta H by dividing minus Q by N. So Q equals mc delta T has M as the mass of the water heated, as the temperature change in Kelvin is delta T, and the heat change in joules that falls out of that is Q. So let's have a look at a 4-mark example question. So first of all, it tells you what the student does. They add 25 centimeter cubed of 0.512 mole per decimeter cubed of silver nitrate to a polystyrene cup. The student measures the starting temperature, then adds a small spatula measure of magnesium. So this particular setup will be the one that takes place in a polystyrene cup that we talked about earlier. So delta T is the difference between those two temperatures, the initial and the final temperature. So putting Q equals mc delta T down, you can take 25 centimeters cubed and treat that as 25 grams of water, times 4.18 times 28.0, 28.0 being the difference between 47.5 and 19.5. So that gives us 2,926 joules. So it says at the bottom to assume that the density and specific heat capacity of the solution are the same as for water. So therefore we can go to the data sheet and get C as 4.18 joules per gram per Kelvin. So you'll notice on the data sheet, the joules, as opposed to kilojoules, means that the number that comes out of this calculation is in joules. So the next thing to do is to work out the number of moles of silver nitrate. Use volume times concentration because it's a solution. So it gives you 0.0128 moles. Then you have to calculate delta RH. So it's minus Q divided by the number of moles of silver nitrate. Now you convert the Q into kilojoules, so it's going to be minus 2.926, not minus 2926, divided by 0.0128, giving you minus 229. So that would be in kilojoules per mole normally, but we've got to be a bit careful here because the ratio of magnesium to silver nitrate is 1 to 2. You can see clearly there's a 2 in front of the AgNO3, so you need to multiply that up by 2, and that gives you minus 457 kilojoules per mole to the minus 1. So it says an appropriate number of significant figures. I'm going to choose 3 because in all cases you've got 3 sig figs for 0.512, 3 sig figs for 25.0, and for both my temperatures you have 3 sig figs again. So why did I have to multiply by 2? Well, it's a delta RH. It's not a combustion or a neutralisation in particular. It's a delta RH. It's a general reaction. So delta RH is calculated and defined in terms of the mole ratio of the reactants in the balanced equation. So in this case, it's going to be 2 moles of AgNO3. And this species is the only one we know the moles for. So we have to take that into account in our calculation. So in terms of marking points, your first one is for getting 2926. Second one is for 0.0128. Third one is for minus 229. And the fourth one, which is perhaps the hardest one to remember, is to multiply by 2 to get minus 457. Okay, thanks for listening. Until next time, see you soon.